Okay, well, thanks for having me here. I'm going to talk about Drivewyze. We're a local company, started here in Edmonton, and now we've grown to over 200 people. We just opened a new office between Calgary Trail and Gateway at 54th Avenue. So we opened that in March and have been inviting people back to the office, but we're a hybrid workplace. So we have people in the office when they need to be, people working at home, and a lot of people working remotely. But we started in Edmonton. Most of our folks are in Edmonton. So the majority of our development team is here. We have people in Kelowna and Toronto, a lot of people across the US because our big market is in the United States. So we are in the transportation industry. We provide software to trucking fleets. And I'm going to tell you a bit about what we do and how we got here, and focus a little bit on how we built Drivewyze. So that involves solving technical problems that are like functional in nature. How do we actually do what we need to do to deliver a product? It involves scale, reach and scale, from an architecture, a technical perspective on scale, and also from an organization perspective. Those last two, I'm not going to spend too much time on. We're going to spend a little time talking about the problem set, and just introduce you to a couple of the problems about working with trucks and truckers on the road, because the problems are fairly meaty, and it's been a lot of fun to work on that. So I started working in the software industry at about the time that personal computers just became a thing. So I've been doing this a long time and seen a lot of changes, and have also worked in different sizes of organizations, from startups through to like medium-sized software companies up to IBM. So spent a few years here in Edmonton running the software group for IBM downtown. The best experience by far has been at Drivewyze. I've been here for 10 years. The problems are really interesting. The customers are very happy to have what we're providing, and the team is excellent. The leadership team at Drivewyze and the team we've built over the last 10 years is really fun to work with. So let me see here. Let's see if we can get this smooth. So a bit of a serial technology hobbyist. I pick things up and try them for 6 months and then put them in a box in the basement. Probably the hobby that's the most technical, that has been the most persistent, is outdoor photography. I also have a deep interest in languages, and like that's a snippet of Lisp. I'm on my fourth Lisp. So I like to implement languages and apply them. I'll get into a little bit more about Lisp and why that's important to me and to Drivewyze. The Christmas tree, I don't know if I can make this go. Oh yeah, there we go. The Christmas tree is driven by an Arduino with a fourth written in C, tailored to this problem of driving RGB LEDs and brain animations with LED strips. So that was fun. I strung 600 lights through our Christmas tree in December, and it's been a blast. Okay, so who's Drivewyze? I mentioned a little bit about this. We're in the trucking industry. We build software as a service. So we build software and we bring it into truck cabs through a partner network. So we decided 10 years ago that the way to reach truckers on the road was not to sell an application to every trucker, but to reach them through an existing channel. So we started to develop partnerships with manufacturers of in-cab computers. And about 8 years ago, there was or 7, something like that, there was a big, what's called an ELD mandate, electronic logging device mandate in the US. That was a law, federal law that was passed that required interstate truckers to have a computer that tracks their hours of service and is connected to the engine bus, and tracks also when the engine's on and running, when the truck is driving, when it's idled, and so on. So there's a 110-page long set of rules about what drivers can do and how long they have to rest and so on. And this mandate was to enforce that in law. That drove a huge industry change. So electronic logging devices were partly adopted in the industry, mostly big companies and those that had concerns about logistics and wanted to hit with their drivers. But this drove it to 3 million trucks. And that created a gold rush of implementers, and we tested 120 some partners that are the providers of these electronic logging devices, and that industry is going to shake out for a long time. But we have our software integrated into all of those devices. So we're on 3 million trucks right now with our software installed, and running hundreds of thousands of those are active daily. So we're getting a lot of data and delivering applications to drivers. So that choice about how we go to market drove a lot of technology decisions. This was who came from? It might be Paul Graham. I really like Paul Graham. So this might have been something he said, but the idea is that if you want to start up a software company, find a hard problem and then try to solve it. And the harder the problem, the better, because there's probably not too many others trying to solve that alongside you. And the problem we tried to solve was, I can't remember the order of my slides, so we're going to kind of play it by ear here. The problem we first tried to solve was weigh station bypass. So truckers have to stop by law at weigh stations, and there's about 1,200 of them peppered across the US. And they pull in, they join a line, they get weighed, an inspector puts eyes on the driver, eyes on the vehicle, looks for any obvious problems, and decides whether to pull that truck in for a deeper inspection. So that is 2 or 3 times a day. A long haul trucker will encounter a weigh station, will pull in. Sometimes it's a 10-minute, join the queue and wait, and then you get a wave and off you go. But oftentimes it's a 30-minute delay or a 3-hour delay. And that impacts drivers and whether they get home that night. And it also impacts fleets and how much they're spending to keep trucks, idle when they're hopefully are fit trucks. So weigh station bypass is a solution that's been out for about 20 years. The solution, the incumbent solution, was built in a sort of public-private partnership, and it's a transponder-based system. So an RFID tag goes in the window of the vehicle, and they have gantries and readers and drive that way. And the little thing in the window will give a green light if you can bypass the weigh station, or a red light if you have to pull in. So very simple old technology. And very expensive to implement. So in 10 or 15 years, that company had managed to deploy about 300 weigh stations with this, and they'd invested hundreds of millions of dollars to do that. We wanted to come in and leverage the computers and the cellular network and the GPS that was already in the truck, and provide the same service, but do it with software and deploy it instantly. So we started to build this Drivewyze Pre-Clear, which is the weigh station bypass. That's still our flagship product. The bulk of our revenue comes from here, and it's a very sticky solution. You get this into a truck, and the drivers love it, and they never want to let it go. So we have very, very good adoption, and we have, like I said, this big network of partners that want to see this on their devices. So that's our first product. And that grew over a 10-year period, somewhat organically, but a lot of effort was put into growing that network so that we now cover almost every state. And Canada's a little bit pokey, two provinces, but Canada has a disadvantage in that there's no federal programs or oversight. Everything's at the provincial jurisdiction. So it's harder to get in there. And Canada is generally a little bit more conservative about technology adoption. But that's how we grew that network. And now once we had that network in place and presence in all of these trucks, we could start to think about other products, start to branch out a little bit. Safety products, we're monitoring GPS in the truck so we can notice when a truck is approaching a hazard, like a sharp curve that's not well marked, or a place where there's a history of rollovers. a place where there's a history of drivers not being aware of the speed change. So there's a lot of different sorts of hazards that are very static in nature, and then we started to build those out as geofences that get pushed out to those devices and activate different alerts for the driver to warn them to these situations. We found, analyzing the data afterwards, that these programs can be really, really effective. Our first data set was on high rollover. If a driver receives an alert warning him of a dangerous curve versus a driver that doesn't see that alert, we saw about an 11% change in the speed of the vehicle through the curve. And 11% when we're talking about, lateral acceleration and tipping hazard, and it's a big deal. That's a big change. The whole program, we did a little study recently with a big customer and compared our ranking of driver behavior at these hazards and their history of, trucks getting tangled up. And we found that trucks that we ranked as the riskiest drivers with this program were 4 times more likely to be involved in a crash. So that is like 4 times more likely that's a huge deal for fleets, for drivers, for insurance. It has a lot of impacts. And then finally, one other product, EInspection is a new thing. I don't know what that red line is, but I think it's going to be with us for the duration. So EInspection is an offshoot of the Way Station Bypass, but this is a new program, and it's one that we proposed to the Federal Motor Carrier Association in the US, a federal agency that oversees highway safety, and actually got legislation changed to support electronic inspections, either as a pre-filled inspection report, where we're pulling data from different enforcement systems and giving it to agents. So a 30-minute inspection takes only 10 minutes. Or what we're driving for a little bit longer term is an electronic filing of voluntary disclosures from the fleet as a truck is approaching a way station. And that voluntary disclosure resulting in the fleet being credited with a partial inspection. So it's as if they stopped and as if an officer looked them over, but they didn't stop. They continued right past the jurisdiction. So we go from a flagship product to branching out into other areas that are adjacent to actually impacting the industry and changing the way that that highway safety is being carried out. It's been an exciting 10 years. 10 years is a long time, but it goes by pretty fast. So, okay, so back to the hard problem. Picking a hard problem, then solving for the product domain issues. How do you make it work? And you just make it work with one truck, and then try to get that to scale. So with Preclear, we had to solve that problem. I'm going to go a little deeper into one of the technical problems that I think is it's a favorite of mine. It's a little bit interesting. And then once you start to get some traction, pretty quickly, the amount of data that's flowing, it grows faster than we were expecting, and in ways that we weren't expecting. So the second issue is, how do you scale your architecture to accommodate that volume of your success? And then the third problem, which is actually, I think, the hardest of these, is scaling the organization. How do you grow an organization of developers and keep them talking and keep them moving quickly? Because when you have 6 developers in a room and a whiteboard, and you're trying to do the first part of solving the functional aspects, everybody's talking all the time. It's really easy to communicate. But when you grow to 60 people or 100 people, and you're spread out geographically, that becomes a real problem. Not just how do you keep people talking, how do you keep people from stepping on each other's toes, how do you work in the same code base without having conflict, how do you handle the combinatrix problem of testing. So there's a lot of issues to scaling an organization that I think are a lot harder. I like the first one, and I try to keep myself stuck in the first one and try to find new problems to work on. But we have lots of people that are really expert in these other areas as well. So I'm going to focus mostly on the technical, the first part. And there's a couple of elements to this. The first ones on this list are a result of our go-to-market strategy. So we wanted to go to market with partners with existing hardware that's already in trucks. Some of that was already 10 years old in the truck at the time. And so there's a sort of a hardware capability problem. This is a mature market. Truck drivers don't really care about technology very much. They just want to get their job done and get home. And they don't have a very high tolerance for startups and, we'll try something different. So we knew that we needed to have a solution that would work well and that would work, if not on the first day, then we'd be able to iterate quickly. So iterating quickly with these partners was a huge challenge. We're talking about a mature industry with partners that have themselves hundreds of thousands of devices in the field that they're managing, and a diversity of hardware. They move very, very slowly. They were surprisingly liberal about letting us put software onto their devices. Didn't really want to test it very much, but they moved very, very slowly. So our cycle time to build something, get it to our partners, get it onto some trucks, it would have been something on the order of a year. So you can't build a startup with a cadence of a year between attempts. To solve the problem. So that was a really big problem that we could see right away. And anyway, with device constraints, high data cost at that time, a lot of our partners had cellular data plans that were pooled, that were very low amount of data per device. So we had to fit within their budget. And who knows what. And then we didn't even get into the product domain problems. What are we trying to solve? Are we doing the right thing? How are we trying to solve that? So that's a whole set of problems. These ones above are more platform domain. And then the product domain ones were layered on top. So, like I said, the biggest challenge we had was operating a lean startup. If you've seen the book or been exposed to the concept of the lean startup, it's iterate quickly. Do something minimal, get it in the market, find out what works and what doesn't, iterate. And so we want a cadence of like 2 weeks, not a cadence of 6 to 12 months in order to do that. So that was number one challenge. So this is a Paul Graham quote. I love this quote. I discovered this after we built everything, and I started to do some research about how we solve the problems that we solved, and Paul Graham kept coming up. So I started reading some of his things. But he said, solve problems by first writing a language, 4 problems of that type, and then write your specific application in that language. So that's what he's talking about here is bottom up and top down programming for design. And he advocates a method of solving your problem in the application domain, but also pushing things that make sense down to the language. So building the language that you're writing in at the same time as you're building the application and sort of converging. And you do that with a tailored language or a language that is very tailorable. So what did we end up doing? What we ended up doing was building an SDK. Our first partners, we built a library, and we've also built the software for the end device. So our first 3 partners, we built the whole thing, we handed it off, and we pushed it out to their fleets. Once we were ready to expand our partner channel, we couldn't scale that. So we knew we needed to have an SDK that was more turnkey, that's easy to integrate, that we can ask our partners to do that integration work for each of their specific devices. So we ended up with a SDK built for those in-cab devices. The release cadence was still a concern. So those were built to be efficient, to take care of the varied capacities of those devices, to be agile, where we could control ourselves, our cadence of development. Once that SDK was in place, we never needed to touch it again. And shelf life. So we still have 2014 era integrations that are running on the highway. So that's a pretty good shelter. It's not comfortable to have 10-year-old software in the field, but it works more or less. So the SDK we built is a combination of native code. It's written in C# and then the second version in C++ with platform wrappers around it, and an embedded scripting language, which was a dialect of Lisp that we built a Lisp interpreter to be compact and efficient and tailored to our problem, which is GPS and geofences and events. So that language choice was mostly by accident or by, I guess, just being observant of noticing what we were doing and how much it resembled Lisp. And then saying, okay, well, if this already resembles Lisp, let's lean into that and go in that direction. So we have a Lisp interpreter in 3 million trucks that operates on real-time events, transforms them into other events, and drives the UI with the driver and drives communication to the client. Right off the bat, because of that shelf life problem, we wanted to load it up pretty heavy. So this was not an MVP kind of an approach. This part of our solution was built to last. It was over-engineered in a significant way. There's 20 ways to do most things. And that's really great because at this point, we have a list of 30 or 40 defects in that original code that we can never fix. And so we have enough workarounds and enough alternatives to be able to live with them. So that was a case where lean doesn't quite work, and we invested about 9 months in the first version of that SDK, which was a little tough. There was a bit of pressure to move faster, but we built it well for that time. Okay, and then the domain logic, the product domain logic is built in this sandbox scripting language and synchronized to vehicles over the air. So every vehicle that's on the road contacts our servers, usually at least every hour, sometimes more frequently, and we keep updating the scripts, we keep updating the geofences. It all happens over the day. Okay, that is the big technical approach. The event-centric approach is just a way of decomposing the logic and splitting off the UI piece from other pieces. So that's pretty straightforward. The weaker CPU devices, we manage that by just managing the amount of time, the word processing limits on how much time we allow. So we allow a certain amount of processing time, and we give significant amount of time back to the device for the other 80 applications it was trying to run. And the data cost problem we managed with the local object cache, just storing JSON objects locally and synchronizing changes. So those are kind of the highlights of the technical approach that we took. So now I was going to switch. Oh, and by the way, if anybody has any questions, just dive in. I'm going to keep on running like a locomotive here to get to the end of these slides. But yeah, I'd be happy to stop and talk about anything you want to talk about. Okay, I was going to turn now to these guys. What they're doing is they're installing a weigh motion scale into a roadway. So this is a piezo sensor that a truck drives over at highway speed, and then kind of goes thump, and it measures the weight of each axle as it's driving over this. This is very commonly deployed. They're used in enforcement. They're used in traffic management. There's thousands of these systems on the highways. So this is a requirement for about a third of the weigh stations that we operate in, that we have a real-time weight for the truck. And that's how we get it. So this device delivers weights of every vehicle that drive over it. And then we have to figure out which weight that's been delivered is the weight of our truck and do it all in real time. So the challenges here are more to do with how we do this in real time. So typically what we see is a weigh motion installation. It might be just in lane one. It might cover 2 lanes. There might be, there's usually going to be a vehicle classifier, which would be a set of loops that measure the length of the vehicle and the speed. So it'll see a vehicle drive over and say, this vehicle is going 30 meters per second, and here's how long between, when it entered the loop and when the tail of it exited, but it gives a length. And length is used to classify, length is used to classify vehicle, and partially it's axle count and the axle spacing. So these weigh motion systems, they live in a cabinet on the side of the road, and they read all this data and they deliver XML scale readings that include the vehicle classification, axle weights, and a whole bunch of weight rules that get applied to all of that. That data, usually what happens with this is these systems will be self-contained. So there will be a collection in here, and then some distance down the road, there will be an electronic sign that says pull in or bypass, basically. They direct the trucks to different lanes. So a vehicle that drives over one of these that's overweight would be directed to one lane. Vehicles that read a good weight will be directed to a different lane. Our competitors in this integrated with us by putting another gantry at the top of this whole thing and a transponder reader. So now what they're doing is they're getting the weights off the scale, and they're doing the transponder reading and synchronizing that data together and using that in rules. What we're doing is we're doing it with GPS. So we have a GPS stream. Every second we get a GPS point inside the vehicle, and we would build a geofence around this thing, and we would collect all the GPS points every second. So usually about 8 or 10 points. And then that would go over the cellular network to a server. We put another little computer in the WIM cabinet to get the scale readings up to our server. And then we match that together and say that is this good. And that gives us a vehicle. There's a few complications. These classifiers, they don't work that great. Some of the early devices have wonky clocks on them. So, if we get a GPS timestamp, presumably that's nanosecond accurate. Yep.
Yeah, I was wondering, how did you solve two trucks going right next to each other?
Right, good question. So yeah, I'll try to answer that. So these challenges, the clocks in the devices, sometimes lane discrimination, we can't tell if the truck is in this lane or that lane with the GPS accuracy we have today, or at least not easily. The cellular connection, sometimes a modem would take 8 or 10 seconds to warm up and connect to a tower. At that time, the truck is 500 meters down the road. So there's a lot that goes on here, right? The lane problem is one. And it happens more than you might think. A truck who knows he's over will pull up beside another truck and just ghost him through these lane motions. So really, we're getting, in a lot of situations, we're getting classification data from all these lanes because that's fairly cheap to install. And so we would say, is there a truck in lane 1? Oh, there's a truck in lane 2. We have inconclusive weight. So, we would give a weight if we're confident. Otherwise, we don't give a weight. And then it's up to that jurisdiction to apply the rules that they want to apply to that. So if the rule is a percentage of pull in or 100% pull in or whatever, they would make those decisions. Okay, so some of these problems were, harder than others to solve. The clock one I referred to, this is a 10-year ago problem, but it was so hard. I really enjoyed trying to solve this one. So sometimes we would see not a GPS timestamp in the data we're receiving, but a system clock for God knows what reason. They would overwrite the GPS timestamp with a system clock timestamp. And the system clock is operated by a crystal. And the crystal is kind of accurate. So what we would see is a persistent drift in the system clock over time, and then periodically a sudden correction. So these ELD manufacturers were running software to synchronize the system clock to like a global standard, but only every couple of days. So we get 2 days worth or an unknown amount of drift in the clock, and then a sudden correction. So that made this problem a little bit harder. The worst devices would have a drift of up to about 15 seconds. So you imagine how many vehicles could drive through an area in 15 seconds. So it really depended on what we could provide here. It would depend on the road conditions, how many trucks were on the road. You know, if we had a big enough window, then we could give a pretty confident weight. But this was a pretty ugly problem. What's next? Oh, and here's another one that was a little ugly. This is a case of using statistical methods to solve some of these problems, because we had a state where we were trying to do a blind association. So we would have a truck approaching a sensor, but there's no vehicle classifier. There's nothing to tell us that it's a truck and not a passenger vehicle. So now we were dealing with the density, not just of truck traffic, but of all traffic, and trying to decide when to trigger an association with that sensor. So what we ended up trying to do was we built like this sort of conditional probability. If we see a vehicle in a given window size at the sensor, and given the density of traffic that's typically there, what's the probability that we are seeing the vehicle we want? So we started with this as a model and took it pretty far. It hit a lot of the data to get me here, but what we ended up with was identifying like a sweet spot that would balance the likelihood that we would make a successful association in that time window against the chance that it's actually the wrong vehicle. So if there's more traffic, we have a bigger chance of having a different vehicle in that window that we were looking at that sensor. So this was kind of a difficult problem. And this is a different kind of difficult problem. So this is an exchange on the New Jersey Turnpike. And it's an absolute spaghetti mess. So GPS data within this is, it's certainly a value. Like the GPS accuracy is typically 10 to 15 meters. You see by experience, but trying to figure out, depends on what you're trying to do in the product problem, but trying to figure out exactly accurately like when a truck is on a given road. There's a toll road running through the middle of this thing. So, is he on the toll road, or is he on an adjacent road, or is he maybe even on that frontage road that runs parallel to this for quite a long time? So there's a lot of situations like this where you have to be creative about how we decide if a truck is on a given road or whatever. Sometimes there's a little bit of experimentation with pulling the view back to where the roads are centered and tracking that the vehicle is on a given road, and then following his possible movements and looking at bearing. So if the truck approaches the ramp, we can often tell if we took the ramp with just a 2-degree bearing shift. And that seems to be a pretty interesting, additional approach to this. But this is an example of what's out there for GPS. Yeah.
So is this more relevant to like the safety product with like the sharp corners and stuff rather than like the weighting?
Right. Yeah. So there's the corners are here for sure. There's a lot of sharp turns in here. But this is also relevant to toll. We just a month ago announced a partnership with a toll provider. So now we're looking at toll deeply. And yeah, there's a toll road running right through the middle of this. So how do we know if you're on the toll road or not with GPS alone? That's a difficult. Oh, sure. Yeah. Oh, yeah, go ahead. Oh, okay. So yeah, in this case, there's 3 or 4 levels here. We don't really have a Z-axis to work with. So usually what we're working with is the bearing of the vehicle. And that we can be pretty narrow about it. So all of our geofences generally will have a bearing filter. So the vehicle, if you draw a fence across this road and the vehicle crosses this way, it's perpendicular. The bearing's going to be off by such a big amount that you can exclude that vehicle. But even in situations like this, you get a road here and a road here. you can either draw the fence, tightly in here where there's the gap, or you can do some testing on bearings. So, you'd see like a, I don't know, 10 or 15 degree difference in the bearing there. And that's enough but this kind of thing, you have to work out, how are we going to solve this? What's the best way to solve it? So we want to be able to get accurate data. We also don't want to lose anything. We don't want to have our filters so tight that we end up accidentally losing vehicles that we should have seen. So there's always a balance in situations like this. Okay. Here. Okay, so I was going to talk, I got one slide on scale and one slide on the organizational stuff. And then we'll just open for questions. So the scaling things, these are the technical impacts of scale. So the obvious ones are the first box here. How many events, how many data elements are we processing? Currently, we're under 1,000 per second, which is, reasonably good scale. But we're growing. So we're growing in this dimension of how many trucks are actively on the road that are running our systems. That's a fairly predictable growth. How much are we selling? We know how much to expect that to grow. We're also growing in a product dimension. We're introducing new products. So now we're introducing a new product. We're introducing new load that is mixed in with the old load and is multiplied by every truck that is receiving that product. And then we also now have a performance dimension where the performance demands of some of the applications that we're looking into are much higher than what we've done so far. So I don't know if I have a slide on this, but for example, a lot of our safety product and the waste station product, those things don't really move. So those are static points of interest. And those can be updated over the air to trucks on an hourly kind of basis, and only for the trucks that are within an hour of driving distance, for example. So there's relatively easy way to limit that. The more dynamic applications like road traffic congestion, that's a more volatile data that we need to be communicating with trucks more on a 5-minute or 3-minute cadence. And there's even more interesting applications like emergency vehicles. So if there's an emergency vehicle, that's not even a point of interest, that's a vector. So we've got a moving vehicle, like an emergency vehicle or a snowplow. Snowplows are a really big deal in states that have snow. That's a huge, heavy vehicle. It's moving down the highway just a little bit slower than highway speed, and leaving a cloud in the visibility. So when a truck tangles with a snowplow, it's a massive disaster. So warning trucks about snowplows that are ahead and are on their route is a really interesting application. But for that one and for emergency vehicles, we're talking about even lower latency, where really we need to push data to vehicles and be able to predict their location reasonably accurately. So the performance dimension means that for every vehicle on the road, now we're receiving data maybe every 5 minutes, every minute, instead of every hour. So that is a huge impact to scale. So the scale of our systems has to be like it's the product of how many vehicles, how many products, and what's the most frequent contact per hour. So that all goes together. So our 1,000 or less than 1,000 events per second could easily grow to 20,000 to 30,000 in the next 2 years. So that is, that's a really big amount of growth. And we can't deal with that by taking everything we're doing now and just growing it by 2 orders of magnitude. So we really need to be looking at how to separate these different loads and how to process them each in exactly the right way that each of those loads requires, and not just try to lift everything. Okay, products and portfolios and scaling. So we have a lot of trucks on the machine, a lot of fleet customers. So now we want to offer them new products. So how much do we invest in new products? How much do we have to invest in keeping the lights on for what we're doing? how much do we want to explore new adjacent markets versus exploiting the ones that we're already in? So those are all product questions that they impact what we have to do on the development side as well. Okay, that one I talked about. This virtuous cycle thing is really interesting. So there's a concept called product-led growth where you take data from an existing product and use that to recommend new products. That's a way too simple an explanation. I need the VP of product here to talk about it, but the idea is that we have a critical mass of data and customers, so we can identify which of those are good candidates for other products and approach them in a product qualified kind of a manner. So that's a really great way to grow quickly. That means that you can grow quicker, which impacts scale. And there's also this sort of interplay between having a lot of vehicles on the road that we can reach and having agency-sponsored safety programs. So a lot of states, the snowplow problem is one example. So states want to solve the snowplows. They really want somebody to be able to tell commercial truck drivers that there's a snowplow on the road ahead. There's no way to do that. There's no way to reach those trucks. Well, we provide that. So we have this diagnostic solution that reaches across all the different hardware platforms that are in trucks. So we can reach a lot more trucks than any one of those individual providers can. And so the state agencies are very interested in that. So they want to pay to have these solutions built, and then fleets see the value of those solutions, so they want to sign up. So the two things support each other and they grow together. Okay, so that's system scale. And very, very briefly, organizational scale gets really complicated. We're not one development team anymore. So what we're trying to do is adopt a sort of a data mesh inspired structure. So we have platform aligned teams that are building the basic platform. So they're building the SDK that goes into the truck. That's platform. They're building the event infrastructure and the cloud and how microservices attach and portals get built. That's all platform. They're building the data infrastructure. How do we process data, do ETLs, MapReduce, all of that stuff. So that's all platform. And then product aligned teams will use all that platform capabilities to build their specific product. The idea is that product aligned team should be able to own every work product that is required to deliver their application. So they need to build a portal, they need to build the ETL, they need to build the scripts that go into the trucks and so on. So they need support for that, and that's where the enabling rules come from, and then governance drives it the whole thing to make sure we're applying policy correctly and so on. That's complicated. And then on the operations side, that also has grown a lot. We don't have one operations team anymore. We have a whole bunch of teams. So all these folks, like there's I don't know, 75 people on that slide, and they all need to be talking at the right time and sharing information and collaborating. So that's a problem. That is not my strength, but we have the right team to do that. All right, challenges. I am out of time, but multidimensional growth. On the product side, data growth, aggregations that we produce and multiplies the data growth even more. Team independence and action, having boundaries between teams, having them be able to articulate what they own, and network effects. This is a quote from inside the company. Companies like ours generally don't starve; they die from indigestion. So, how do we pick our fights? How do we choose what opportunities to go after and what ones to pass on? That is a bigger problem than strategy for the next sale at a certain point in the scale-up journey. All right, then briefly, I knew I'm in a company of AI and ML folks, and we have a very rudimentary machine learning practice. We don't really do much. All of the problems that we have had to solve have yielded to algorithm or statistical or probabilistic methods, and we haven't really delved very far into machine learning. But there's a lot of problems on the horizon that I think do require that kind of approach. So we've needing to start to build that capacity. So, some of these things we're starting to put a lot of alerts in front of drivers. How do we pick and choose? How do we discriminate what's a valuable message for a driver from one that maybe he's seen it 100 times, maybe, there's no chance or very little chance that if he drives for it, that he's going to take that turn. There's a lot of things we could do to kind of simplify the driver's experience and not overwhelm the cognitive load inside the truck is as much of a safety, not as much, but it's a safety issue as well as the actual road hazard. Geofence optimization, we plunk the fence down 400 meters ahead of the curb because we think that's right. Should it be 450? Should it be 600? So we need to actually figure that out. Anomaly detection, we have a lot of systems. So how do we go from monitoring with graphs up on a big monitor to monitoring via machine learning algorithm that is looking for any change in that data. The product like growth stuff, recommendations for products, that's probably a good application. We have some specific pattern things like weigh stations. We don't have very good data about if the station is open or closed. Closing a weigh station is an officer flipping a switch and the light down on the highway goes from a green open to a closed. And the trucks will bypass automatic or will bypass the driver will decide bypass because the weigh station's closed. So they close stations sometimes on an hourly schedule, sometimes they will close them because they've got too many trucks on the station that they're looking at and they just don't want to see anybody else. So we don't have good data for that. So that's kind of an important piece of our reporting. If not, it doesn't really drive any logic. The driver risk assessment I touched on, and these last ones, it's not really us doing this, but we're collecting a lot of data about where trucks drive and what roads are in trucking. They're called lanes. The lane would be like the Chicago to Philadelphia road, they call it a lane. And so we have a lot of data on this, but we're not really using it for anything. And there's other companies out there that are trying to solve problems about logistics and optimize the loads and finding a return load for a driver and things like that. So, and then the macro stuff. How do we turn this into economic data that's going to be valuable in other places?